In this video, we're going to go over section 3.5 from our textbook, which goes over implicit differentiation. So first, we're going to look at some special function notation. So for example, if we were given this equation here, this equation will define a function f with y as our dependent variable and x as our independent variable, because as we change values for x here, it'll change values for y. So y is dependent on what we have for x here. Now using function notation, we would write y is equal to f of x, or f of x is equal to this guy here. And so this is just emphasizing that we do have a function of x, or a function that's dependent on our variable x. And so in order to minimize the number of symbols we'll use, we will usually write this guy, equation 1, as this here. And in this case, y is both a dependent variable and a function symbol. So we just have to keep that in mind when writing our equations this way. And so some examples are this here. We have x is equal to 2t squared minus 3t plus 1. And so in this case, x is now our dependent variable, and it is a function of t, where t is our independent variable. So our values for x that we get here depend on what we have for t. And then we would write it like this, emphasizing that x is a function of t. And similarly for these two equations, z and r, that we have here. Now, we've only really considered functions involving one independent variable, and these are some examples that we saw here. However, this function here, we have f of x, y, so this is a function emphasizing that it's dependent on our x and y values, is equal to this guy here. So this function will be a function that involves two independent variables. Okay, so now let's look at this equation here. We have 3x squared plus y minus 2 is equal to 0. And what we can do is solve for y in terms of x, and we have a function that is dependent on x. And so equation 3 and 2 here both define the same function with x as our independent variable and y as the dependent variable. And so we would write it like this to emphasize that. And in this case, we have what's called a explicit function. So what this means is that our function is directly stated, so the rule that's stated, which enables us to determine y for each value of x. So pretty much our function is our rule. Our y is going to be depending on what our values of x are. However, in this case, for equation 2 here, the y is the same as in equation 3 here, but equation 2 implicitly gives, or pretty much implies, but does not directly express y as a function of x. And we can see that here just by looking at this. It's not clear immediately that y is a function of x, but it is implied. So in this case, we would say that these functions 3 and 4 here define function f explicitly, and equation 2 here defines it implicitly. So we can do some color coding. These are explicit functions. And equation 2 is an example of implicit function. All right. So using an equation that defines a function implicitly to find the derivative of the function is called implicit differentiation. And that's what today's video is all about. So looking at the same equation that we had before, what we're going to do is differentiate it implicitly. So we'll differentiate equation 2 implicitly, and equation 3 directly. So first we'll start with our implicit function, and we're thinking of y as a function of x, and so we could just change notation here, so that's all we're doing, just writing y as a function of x. So then what we'll do is we'll differentiate both sides with respect to x, so we'll take d dx of our function on both sides here. And we know that we're essentially distributing this d dx to every term in here. So we end up with the derivative of 3x squared, that would be 6x. And then we're left with the derivative of y of x with respect to x. And so we can just write this as y prime for a simpler notation. We know that dy dx is the same as y prime. And then we know that the derivative of 2 with respect to x is 0. And then we also get 0 on this side as well. And then our last step in this case would be to solve for y prime. And so we can do that just by subtracting a 6x on both sides, and so we get y prime is equal to minus 6x. Okay, so that's how we would find y prime with implicit differentiation, or dy dx. But notice if we were to start with our equation and just solve for y, so we add 2 on this side and subtract 3x squared on this side, and differentiate each term with respect to x, we do end up with the same answer here. So you might be wondering why we're interested in implicit differentiation and why can't we just solve for y like this every time? Well, sometimes there will be equations that are either difficult or maybe even impossible to solve for y in explicit terms of x. So in those cases, that's where implicit differentiation will be useful. Okay, so let's get into some examples. Oh, there we go. So suppose we're told this graph here, or we have this graph here, and we want to find y prime by implicit differentiation, and then find the slope of the graph when we have that x is equal to 5. So we know immediately that we are going to do implicit differentiation, and I'm going to do the first step that we did in the last example, which is just rewrite y as a function of x. So we have x squared plus y of x squared minus 169 is equal to 0. So this whole thing is squared. And so what we want to do is find the derivative of this function, So we'll take the derivative with respect to x on both sides. All right. And so we'll do this by essentially distributing this to each term here. So what I mean is we'll take the derivative with respect to x of x squared of y squared of 169 and of 0. And we know that the derivative of 0 is just going to be 0, so I'm just going to write that there. All right, so the derivative of this guy with respect to x is just going to be 2x, that's just power rule. Now in this case, we want to find the derivative of this guy. It becomes a little tricky, and that's because we have this power function here, right? So we're taking, this power function here tells us that we're taking the function y of x to the second power. And in that case, we have a composition of functions, and we're going to have to use the chain rule here, right? So if you remember from a few videos ago, if we have a composition of functions like this, so f of g of x, then the derivative of that will be the derivative of our outside function evaluated at our inside function times the derivative of our inside function. So in this case here, we will take the derivative of our outside function. So we just have a power function, a square here. So we know that 2 comes down in front, and this will be evaluated at our inside function, which we know is y of x. And then we need to multiply by the derivative of our inside function. And so we know that's just dy dx. All right, so this is one whole term that we find using the chain rule. And then we know the derivative of 169 is just going to be 0 because it's a constant. And that'll all be equal to 0. Okay. So then, remember what we want to do. We want to find y prime. And looking at our notation here, we have 2x plus 2y of x times this guy here, which is y prime. So what we'll do is we'll solve for y prime. And then actually we can also write this as this here. So we can drop this function notation here. That's just used to emphasize that y is a function of x, but we can also write it like this. And sometimes this is just a little cleaner, easier to work with anyway. So I'll leave it at that. Okay, so we're just going to solve for y prime. So we'll subtract 2x on both sides. So we get 2y times y prime is equal to minus 2x. And then solving for y prime by dividing by 2y on both sides, we get negative 2x over 2y, and so we get negative x over y is equal to y prime. All right, so we found y prime by implicit differentiation, and we also want to find the slope of the graph when x is equal to 5. So we know that this is, our y prime here is the slope of the graph. We want to find that when x is equal to 5. So we can plug 5 in for our x value here, but we aren't given a value for y. So before we can do that, we need to figure out what value for y that we get when x is equal to 5. So, and I'll put that over here. So at x is equal to 5, what we want to do is find what is y equal to. And so we'll do that by plugging in 5 into our original equation. So we'll do 5 squared plus, minus 169. That's going to be equal to 0. Then we have 5 squared, which is 25, minus 169. So we get minus 144 here. It's going to be equal to 0. Then we get that y squared is equal to positive 144 by adding 144 on both sides. So then this tells us y is going to be the square root of 144, and this will give us plus or minus 12, because we know that positive 12 squared is going to be 144, and then negative 12 squared is going to be 144. So this gives us 2 points. We have 5 and positive 12, and 5 and negative 12. So what we're going to have to do is evaluate our y prime here, our slope at both of these points. So I'll write that here. All right. So looking at the first point, and this is what's called an evaluation bar. So when we write this, what I mean is we're evaluating y prime, and this bar here tells us at what point. So y prime evaluated at 5, 12. All right, and so just plugging in 5 for x and 12 for y, we just get negative 5 over 12. All right. And then doing the same thing for our other point, 5 and negative 12. So we're evaluating y prime at 5 and negative 12. We will plug in 5 here and negative 12 on the bottom, so our negatives will cancel. And so we get positive 5/12. All right, and then here in the left-hand corner is a graph of our function, and so we have a circle here. So it makes sense that at 5 we would get 2 values for y. And so we just found that at 5, at this point right here, the slope of our tangent line, so our line will look something like this, is 5/12. And then our second point, so at negative 12 down here, the slope of our tangent line is negative 5/12. All right, and then just going back to our original question, we were told to graph this, and I provided the graph for you. And then we wanted to find y prime, so we did that. And we wanted to find the slope of the graph when x is equal to 5, and we did that there. All right, so that's it for that example. Let's look at another one now. What we want to do is find the equations of the tangent lines to the graph of this guy here at the points where x is equal to 1. Okay, so we know the equation for the tangent line. We know we're going to have to first differentiate this guy. So take the derivative of both sides of this equation here. And so this is an implicit function here, and x is going to be our independent variable. We could potentially solve for y, and the values of y will change for different values of x. But for this, we do want to take the derivative of this using implicit differentiation. And so we are differentiating with respect to our independent variable x here. All right, so we're going to do the same thing we did last time. We're going to take the derivative of each of these terms here. And we know that the derivative of 0 is just going to be 0. All right, so the derivative of x squared with respect to x is just 2x. The derivative of this guy here with respect to x, we saw in the last example, using the chain rule, we get 2 times y of x times the derivative of y with respect to x. And then we want to find the derivative of this guy here. So something to notice here is that we have the product of two functions. We have x times y. So this immediately tells us that if we want to find the derivative of the product of two functions, we're going to use the product rule. So our first function is x, and our second one is y of x. So what we'll do here is we'll write this out. We'll use big brackets to separate these guys. So remember, using product rule, we'll take the derivative of our first function and then just multiply by our second function. So we'll take the derivative of x, and then we're just multiplying by our second function here. Then we're going to add the derivative of our second function, and then multiply by our first function. Okay, so we're just using the product rule here, and then these are our two functions. And then we know that the derivative of 7 is just going to be 0 because it's a constant. So this is going to be equal to 0. All right, so let's simplify and maybe write this out in nicer notation. So I'm going to change all of my y of x's to just y. We know that dy dx is y prime. And then we have this guy we want to simplify. So we know that the derivative of x with respect to x is just 1. So this term is just 1 times y of x. And I'll just write that as y for a simpler notation. And then we know that dy dx is just y prime. And then we're still multiplying that by x. And this is all equal to 0. All right, so not too bad. So then we get 2x plus 2y times y prime minus y prime of x. So just distributing this negative to both terms in here. and this is all equal to 0. Now we want to solve for y, and so I see two terms here that solve for y prime, and I see two terms here that have a y prime in it. So what I'm going to do is take the two remaining terms that don't have a y prime and put them on this side. So I'm going to subtract 2x from both sides, and then I'm going to add y to both sides. So we get 2y, y prime, minus y prime of x is going to be equal to minus 2x plus y. All right. And we also have a y prime in both terms here, so I can pull that guy out. And we're left with 2y minus x here, and that'll be equal to 2x, or minus 2x plus y. And lastly, solving for y prime, we'll just divide out this 2y minus x term on both sides. And so we get y prime is equal to minus 2x plus y all over 2y minus x. All right, so this is our answer for y prime. Remember, we want to find the equation for the tangent line of this guy at this point, x is equal to 1. And so we would plug x into here, but again, we don't have a value for y. So we need to figure out what y will be equal to when x is equal to 1. So plugging x is equal to 1 into our original equation here and solving for y, we get so this becomes 1 plus y squared minus y minus 7. So we get y squared minus y minus 6. And then we can just factor this guy. So we need two numbers that multiply to 6 and add to minus 1. So we get negative 3 and positive 2. And then this tells us that when x is equal to 1, we'll have 2 points. We'll have negative 2, and we'll have positive 3. All right. Now what we want to do is find the equation at these points. And so what we'll do is point-slope form. So we have 2 points here. We have the slope here, and so we just want to evaluate the slope at these points and then use point-slope form to get our equation. So we'll evaluate y prime at 1 and negative 2. So plugging these values into our y prime. All right, so we'll get negative 4 on top, and then negative 4 minus 1 on bottom. So we have a negative 4 over negative 5, so this is just a positive 4 over 5. All right, then doing the same thing for our next point here. So just plugging this into our y prime. All right, so on the top we get negative 2 plus 3, so we've got 1, and then on the bottom we have 6 minus 1, so we'll get 5. All right, so this is the slope of our tangent line at this point, and then this is the slope of our tangent line at this point. All right, so we have 2 points, we have 2 slopes. Now we'll just use point-slope form to find our 2 equations. So I'll do our first point, and we'll use point-slope form. So just as a reminder, it's y minus y1 times, or is equal to m times x minus x1, where m is our slope, and then our y1 and x1 is our point here. So plugging this in, we'll get y minus y1, which is -2, is equal to our slope, so 4/5, times x minus x1, which is 1. So then we'll get y plus 2 is equal to 4/5 times x minus 4/5. And then solving for y, so we'll subtract 2 on both sides. And then we'll find a common denominator for our two fractions so we can subtract them. So I'll do that by multiplying this by 5/5. So then we get this equation for one of our tangent lines at this point here. And then we'll do the same thing for the other point we have at 1, 3. So plugging this in again to our point slope form. Oops, sorry, this is 1/5. So we'll get 1 over, sorry, I'll add 3 to both sides and then distribute this guy to both terms. I'm trying to do everything all at once. So we'll get 1/5 x minus 1/5 and then plus 3. And then again, we need to have a common denominator here, so I'll multiply the top and the bottom by 5. So we get 15/5 here. All right, so we get the second equation for our tangent line at this point here is given by this equation here. All right. And then we're going to look at one more example here. So we want to find x prime for x is a function of t, defined implicitly by this guy here. So in this case now, t is going to be our independent variable. All right, so we're going to find x prime and then evaluate it at this point here. So we'll start by taking the derivative, both sides of this equation, and remember, since t is our independent variable, we're going to take the derivative of this with respect to t. All right, so distributing this guy, we'll get this here. All right, and we know the derivative of 1 is just 0, so we can leave, this will cancel out. This just becomes 0. And we want to find the derivative of this function x times this function L of t. So we're again going to have product rule, or we're going to use product rule here. So we'll do the derivative of our first function with respect to t times our second function plus the derivative of our second function times our first function. And then we have the same thing happening here. We have the product of two functions here, t and e to the x. So we'll use product rule again on this guy. All right. So we'll take the derivative of the first function multiplied by the second function plus the derivative of our second function multiplied by our first function. All right. So we know that dx dt is just going to be x prime, and then we have multiplied that by ln t. And then we know that the derivative of ln of t with respect to t is going to be 1 over t, and then we're multiplying that by x. And then here, we're going to take the derivative of t with respect to t, so that's just 1, and then multiply that by e to the x. So we get e to the x here. Now, in this case, for this guy, we need to be a little careful. Because we have this function e, also this should be with respect to t. But still got to be careful with this guy. We want to find the derivative of e to the x with respect to t. So in this case, we have a composition of functions. Our parent or our outside function is going to be e to the t, and then what's being plugged in there is x. So we're going to have to use chain rule here. All right, so we know that chain rule will take the derivative of our outside function. So that's just going to be e to the x. And then we're going to multiply that by the derivative of our inside function, and our inside function is just x. Sorry, I keep writing x there. Right? Because remember, our parent or our outside function is e to the t, and then x is being plugged in there. And then this is all being multiplied by t, because we have this t on the outside. So just so we can see what's happening there. All right. So let's simplify a little bit. We have x prime ln t plus, we'll have x over t here. That's going to be equal to e to the x plus e to the x times x prime times t. All right, and now remember we want to find x prime. So what we'll do is we'll move the terms over with an x prime onto this side, and then move the term without an x prime onto this side. So what I mean is we'll take away this term here on both sides. So we'll get x prime ln t minus e to the x times x prime times t. And then I'll take away this x over t on both sides. So make sure I did that correctly. Okay, perfect. So now we have an x prime in both terms here, so I can pull that guy out. So we have ln t minus e to the x times t. And we still have e to the x minus x over t on this side. And then solving for x prime, we can just divide by this guy on both sides. So we get e to the x minus x over t all over ln of t minus e to the x times t. All right. Now what we can do to simplify the numerator a little bit is multiply the top and bottom of this guy by t. So we'll get t e to the x minus x over t. And then this is still being divided by ln t minus e to the x times t, which is the same thing as multiplying by this And so we can write this as this here. All right, so this will be our x prime. And then we want to evaluate x prime at this point here. And so using this notation, so x prime evaluated at 1, 0, we'll just plug in those points. So t was 1 and x was 0. All right. So e to the 0 is just 1. So we just have 1 times 1 minus 1. So we get 1 on the top. And then we have 1 times, 1 times ln 1. ln 1 is 0, so this guy cancels. And then we have e to the 0, which is 1 times 1, and it'll be negative. So our final answer is -1. So that will be x prime evaluated at the point 1, 0. All right, so that'll be it for this video.